Hi, this is Jacob Nash, and in this video we'll be looking at how to find area between curves. So, what does this mean if we're saying between curves? We're basically saying between two graphed equations. Although you might even need to know how to do three, but we're only going to look at two in this video. But anyways, oh, sorry about that. I don't know what happened. Um, so you see we have a parabola right here. And we have just a normal line right here. How could we find the area of the shaded region? Well, what you actually have to do is find the areas under the curve individually and then subtract them. So the area under this parabola, which would be this whole thing, and then the area only under this um, line right here, and then subtract them. If you subtract the full from this one, you'll get what's left over here. So, we don't have to, read all this. Is like just basically the official term, but looking at this, our Riemann sums, we can once again use our the Riemann sums, uh, except we just subtract these from these. So F, so that what this means right here is that whenever you do this, basically the one that's first has to be the one that's on top. So when you're subtracting the Riemann sums, and we'll look at example, the one that's above has to be first, or you'll get the wrong answer. Um, and we do it the same way as we did before. So the steps, we need to know what region it wants us to find. Sometimes it will just be shaded, but sometimes the graph won't even be drawn, and you just would have to know what the different things look like. So, that might be a sign that you would want to review maybe some of the graphs that you don't might not remember. And then you have to figure out where they intersect. That's only if it doesn't shade. So like in this example, you wouldn't have to do that because it already shows you. But if you don't know the areas where they intersect, set the equations equal to each other. Then you have to make sure if what curve is on top changes, and if it does, you'll have to do separate intervals. So let's look at an example. And this is pretty much exactly like what that was. So it's saying find the area between these two curves. So this is a parabola and this is a line, and it tells us the interval. So we don't actually have to, um, we could just use that and know, okay, this is where it is. But if you really wanted to know where they intersect, you set the equations equal to each other, as you can see here, and I move this to the other side, I factor out, and at 1 and 4 is where they intersect, and that works out well because that's the interval it asked. So just by that, we're able to draw a rough sketch, and we can see that for this interval, which it should be marked, but this is 1, this is 4. This is the only region we care about, and the green one is always on top. So we only need to do one interval from 1 to 4. Um, so we just write our integral symbol. We do our interval 1 to 4. Make sure this dx is over here. We will look at an example where you have to integrate with respect to y, which is kind of interesting. But in this case, it's x. Um, and we put our two equations. So first, the one that's on top. The one that's on top is the green, which is this one. So we put it here. We do minus, and then this equation. However, as you can see, parentheses are crucial because if you didn't have this parenthesis here, you might just have only minus x plus 4, which would be incorrect because if you factor this out, it turns into a minus 4 and a positive 5x. Then we do the antiderivative. So this changes to negative 1/3 x cubed. This changes to 5 halves x squared. This changes to minus 4x, 1 to 4. And then when you plug 4 in and then subtract it from once you plug 1 in, you get 19/2 is the area between the curves. So this is a situation where we actually have to integrate to y. As you can see, we have dy, and you might say dy, like, damn, why? Like, and the reason why is because don't these look kind of sideways? That's because they're stupid. Look at these graphs. We have a y to the fourth equals x. What kind of thing is that? Well, you might say, I don't know, but that must mean I need to integrate to y. So that's what I can say. If you don't, if you see something that looks like this, where there's an exponent on a y, and you might not have the graph drawn, but if it is, and you see that it looks sideways like this, you'll know that you need to integrate to y. So once again, if you see an exponent on the y. Um, so let's figure out where they intersect. We set these two equations equal to each other. Um, and usually you do that in terms of like the y, you just get rid of the y's and set the other part equal. But this time we get rid of the x. So we have x here. This one right here, we have to change so it's in terms of x. That's the reason why we can set this equal, because x equals that. So we set both equal to each other. Now we get everything on the same side, and you factor out, just because it's y's, it doesn't change. You still factor it the same as if it was x. Um, and then your answer ends up being negative and positive 1 is where they intersect. And so right here and right here, y equals negative 1, y equals 1. Now we plug it in, so we have the one that's always on top. Now here's the thing that's interesting. You might be like on top because it's kind of sideways. Well, this one is the red one. So the red one is more to the right, so that's what's on top. So it's more to the right. The x values are higher for it, so we put it over here first. Then we do the green one after. Then um, we solve that, and then we change it. We do the antiderivative. That becomes 2y, etc. We plug in these like we always do, 44 over 15. So I showed this example just to show you that occasionally you have to integrate to y. Now, you might also have a situation where what curve is on the top isn't the same. In that case, you have to separate it like you see down here. So let's set cosine and sine equal to each other. They are the same on this interval only at two places, which is x equals pi over 4 and x equals 5 pi over 4. Sadly, if you didn't know that, that means that you really only would know that by knowing your unit circle, and um, that's kind of coming up multiple times already in these Calculus 2 videos. We might have been able to get away with not knowing it super well in Calculus 1, maybe not, but this time there's no substitution for that. There's no other way we can get the correct answer except for by knowing it. So unfortunately, you'll just have to know that. And I plan on making a video in the near future reviewing it because it is not really hard, but it's a lot to memorize or understand. So anyways, we hopefully at least know what the graphs looks like. That's pretty easy. I mean, the way that I always remember it is the cosine, when it's at the y-axis, it's always at 1, and the sine starts down here, and they just make their regular cycles, and they stop, and then they go, and then they stop, and then they go. But the sine is just like a little bit delayed after the cosine. So notice that this high point isn't directly over here because it's only off by pi over 4. That's the thing. It's only off, or sorry, it's only off by pi over 2. It's on, or maybe you would really say ahead. It's ahead by pi over 2. It's not ahead by pi. It's ahead by pi over 2. And pi over 4, halfway in between that, is where they intersect. And they also intersect here. So as you can see right here, green is on top. Right here, blue is on top. Right here, green is on top again, which is why we had to make 3 sections. The first, 0 to 5 to pi over 4. The second, pi over 4 to 5 pi over 4. The third, 5 pi over 4 to 2 pi. And how we know how far to go is because it said 0 to 2 pi. So that's pretty easy. All you have to do is plug in, all right, cosine is on top for that part. Sine is on top for that part. Cosine is on top for that part. And the answer isn't actually given here, but you would do it the same. And you have to know the antiderivatives of your trigs. So cosine, what gets us cosine is if we do d dx sine. So the answer is sine for this. What gets us negative sine? That's if we have positive cosine, because um, positive cosine gets us negative sine, negative sign gets us positive cosine. So that's where it's reversed. So you have to make sure you know that because this can get a little bit sneaky with these negatives and positives, and you could get the wrong answer. So just make sure you know that. The cosine gives us the negative sign. So to get back from a negative sign, we end up with a positive cosine. So then you would just plug in the values as you always do, which once again, you would have no unit circle for. Last example is where you might be told about a shape. Well, you might be like, that's so stupid, but it's actually, if you think about it, a shape really is just like at least a triangle, it can be considered different curves put together. So set up an integral to find the area of a triangular region enclosed by these points with respect to both x and y. Now, so I don't, the whole, I don't know why, but the work isn't completely shown on here. But I'll just basically say what you would do. Because one like this is an S common. But let's see the different points. We drew it. We have 0, 0. We have 2, 2. We have 5, 0. So we see a triangle. But we can really say that this, just make an imaginary line. This is one line. This is one line. So it still is area between curves. It's really just sides. But we have to figure out the equations of these two lines or sides. So how do we do that? Well, first we figure out what the slope is. So down to over 3, negative 2/3. And then you would do the point slope formula to find the y-intercept, which you would just plug in any value you want into x and y to find b, which would end up being 10/3. Then this one is just y equals x. That's pretty easy because it goes up to over 2, and you know this is y-intercept. So these two equations we would set equal to each other. So x equals negative 2/3 x plus 10/3, and then you would find out where they intersect, which I'm sorry, that never mind. That you don't have to do that because you know where they intersect, which is right there. Sorry about that. That's stupid. Um, so now you would just do the same thing that we've done before, but this text is here what's important. If we're integrating with respect to y, which WRT means with respect to, if we're, sorry, with respect to x, sorry. With respect to x, as you can see, the lines imaginarily continue, and right here, this one's on top, and then at 2, now this one's on top. So we'd have to separate it at 2 with respect to x, and that means like we're going this way. But if we do it with respect to y, you don't have to do that because if we're going this way, the lines continue like that, and there's nothing from 0 to 2 that, from 0 to 5, yes, from 0 to 2 in the y direction, it's always this one on top. Or sorry, always this one on top because the higher x is what's considered on top. I know that might be confusing, but just pretend like you make it sideways. Now, the work isn't here, like I said, but you would just do the same thing as like here. For x, we would have to separate, but for y, you don't. That's it for this video. Thanks for watching.